Addition reactions to an alkyne are very similar to addition reactions to an alkene. Let's look at the addition of a hydrogen halide. Here, one of the pi bonds breaks in the alkyne, and a hydrogen is added to one of the carbons of the alkyne, and the bromine is added to another. And which carbon gets what is still dictated by Markovnikov's rule. The rich get richer and the poor get poorer. The triple bonded carbon on the left is the one that gets the bromine. And in the process of the addition, one of the pi bonds is broken, so we're down to a double bond. And the outside carbon is the poor carbon, and it's stuck with the crappy hydrogen. One interesting thing to note is that the hydrogen and the halide go on from different angles. So in this case, if the bromine went on the bottom, the hydrogen that got added from the top. And this will be important when your product is a molecule that has different stereoisomers. So if cis and trans isomers or E and Z isomers are possible, you have to think about this. For example, adding to this alkyne, we will have to think about the stereoisomer that is formed. And we will have to remember that the hydrogen and the bromine come on from different directions. So this would be the product of this addition reaction. And it is a Z isomer because both of the high priority groups are on the same side of the line we draw through the double bond. So the bromine is higher than the methyl. The methyl here is higher than the H in priority. The addition of water to an alkyne is also very similar to the addition of water to an alkene. Here it looks like we're just adding sulfuric acid, but we have to realize this is an aqueous solution of sulfuric acid. It's mostly water, and that sulfuric acid is just there to catalyze the addition of the water. The regioselectivity of this reaction is again dictated by Markovnikov's rule. The rich get richer, the rich carbon gains the OH, the poor carbon is stuck with the crappy hydrogen. And you may be asking yourself, hey look, there's a double bond here. There might be some situations where we have to worry about whether a cis or trans or an E or Z isomer is formed. Well, it doesn't matter so much when the water is added. This double bond actually becomes a single bond. And it's because of a reaction that happens where this hydrogen kind of moves. It becomes bonded to this carbon over here. What I'm about to draw is not highly recommended. I'm going to draw an arrow, but it does not represent the movement of electrons. So don't get confused about that. This is just a movement of the hydrogen over to this carbon. Usually an arrow would represent movement of electrons, but not in this situation. The reason I don't want to draw electron movement arrows is because I just don't want to go into the mechanism yet. That's going to be covered in a later chapter. But anyway, the result of this reaction, this movement of the hydrogen, is a molecule that looks like this. And you see we've formed a ketone molecule. And the story doesn't really end there, because the hydrogen is a bit finicky. It actually will move back and forth, so it will go both ways. So there's actually an equilibrium in both directions here. So it's really a back and forth reaction that's happening really, really fast, back and forth, back and forth. And these two molecules that are in equilibrium back and forth are called tautomers. What kind of tautomers, do you ask? Well, bear with me. Hold on a second. First, let's look at all the names of these functional groups here. A double bond is called an ene. The alcohol gets an ol name at the end of it, like alcohol. And this over here we said was a ketone. So when you put all these together, what you get is keto enol tautomers. But it is the ketone that predominates in this equilibrium. Let's look at another situation where you add to a double bond and you again have to worry about the stereochemistry of the product that's formed. If we add just plain hydrogen, we can work towards saturating the molecule. The important thing is, how do we add the hydrogen? We could do it if the alkyne grabs hydrogens from the surface of a metal catalyst, such as a palladium catalyst, and a certain type of that is called a Lindlar catalyst. Then both the hydrogens come from the surface of the catalyst, which is on one side. So both of the hydrogens are coming from the same side when they add. So what you'll end up with is a cis alkene as your product. But you'll only get an alkene if you add 1 molar equivalent of hydrogen. If you just let this reaction keep going, it will be totally saturated and you'll end up with an alkane, and even your double bond will be gone. Another way to add hydrogen to an alkyne is through ammonia. So in the presence of sodium or lithium and ammonia, the mechanism will be different, and in that case you'll get a trans alkene formed, where the hydrogens come on from different directions. But again, if you provide excess reagents, the molecule will keep getting hydrogenated until it's an alkene. So this is only, or until it's an alkane. The alkene is only formed if 1 molar equivalent of hydrogen is added. There is one more reaction I want to talk to you about today, and it is the most important one. It is not every day that you have a reaction that will make a carbon-carbon bond. So this is an important thing to be able to do, to be able to increase the size of an alkyl chain, to increase the number of carbons in the skeleton structure of a molecule, or increase the size of a alkyl substituent. To make this work, you need a terminal alkyne. The triple bond has to be at the end of the chain. One of the triple bonded carbons has to be bonded to only a hydrogen, because we're going to rip that hydrogen right off. To do that, we're going to use NaNH2. So what that is so you can think of that as being Na plus and NH2 minus. I'm going to write the NH2 minus. That would be a nitrogen with 2 lone pairs bonded to 2 hydrogens. And one of those lone pairs is going to be really attracted to the partially positively charged hydrogen here. And the electrons in the hydrogen-carbon bond go to the carbon. I should write that more toward the carbon. They're going to end up sitting on that carbon. And the result of that is going to be the acetylide ion. And that acetylide ion reacts with an alkane that has a halogen bonded to it. Remember, halogens are pretty electronegative. So what's happening is this chlorine here is sucking electrons away from this carbon. This carbon is therefore a little bit positively charged. So this electron pair on the acetylide ion is negatively charged. It really wants to meet up with something that's positively charged. So it forms a bond with this carbon, and at the same time the carbon has to ditch another bond. And the chlorine's pretty cool with going off and being a chloride ion. And the results of this is our final product. And that step is where we get the addition of a carbon-carbon bond. Or I should say the formation of a carbon-carbon bond. I don't want to confuse this with an addition reaction. So here's your molecule where you've increased the size of the carbon skeleton chain, and maybe it's worth mentioning we also have a chloride ion floating around also. And that is the most important reactions of alkynes.